So our next speaker is David Chan. Over to you.
Thank you. So I'm presenting landmark-assisted Monte Carlo planning. This is work in collaboration with Dana Now at the University of Maryland and Mark Roberts at the Naval Research Lab in DC. So the core motivation for our work stems from the success of landmarks in classical planning. So landmarks, which are intermediate conditions that must be satisfied in any solution plan, have been extremely effective at guiding search in well-known planners like Llama. Meanwhile, planning in stochastic domains, which is often modeled as MDPs, adds a lot of complexity. And in these domains, we have to contend with uncertainty in non-deterministic action outcomes, and large problems quickly become intractable as search techniques struggle to scale. And so the use of landmarks in probabilistic planning has been very limited, so our work aims to bridge this gap. And to do so, we make two primary contributions. First, we formalize the concept of probabilistic landmarks as a natural extension of the landmarks used from classical planning. And then second, we introduce the LAMP algorithm. LAMP stands for Landmark Assisted Monte Carlo Planning, and that leverages those landmarks to guide a Monte Carlo-based search. And it basically decomposes a complex long horizon problem into a series of more manageable subproblems. We're using the landmarks as sub-goals here. Okay, so a quick refresher on landmarks. A landmark in the classical planning setting, I said, is a condition that has to be true in every solution. So in this familiar blocks world problem, if the goal is to have A on B and then B on C, then B on C is a necessary intermediate step. You have to reach a state that satisfies B on C along the way to any solution. So it's a landmark. Furthermore, landmarks can have orderings. These are kind of temporal constraints enforcing which orders or which landmarks need to be achieved in what order. So these relationships are usually captured in a landmark graph like the one shown here. So now, in general, determining if a condition is a landmark is a piece-based complete problem. It's as hard as planning in the worst case. So, but the good thing is that there are algorithms that can find some landmarks for a given problem. And so these landmarks use constructs like a relaxed planning graph or a domain transition graph. Our work uses the RHW landmark extraction algorithm that's named after its authors. But other methods exist as well. The key takeaway here is that we can use any such algorithm to generate this landmark graph automatically for a given classical planning problem. Okay, this brings us to our first main contribution. So we define probabilistic landmark as a condition that has to be satisfied on all paths from an initial state to a goal state for any valid policy. Now, formally, we define this in terms of histories or traces of a policy. Perhaps more intuitively, any path in the transition graph from an initial state to a goal state has to contain a state which satisfies this landmark condition. And so the main challenge in probabilistic settings is how to find these. So, and our key insight is to use the all outcomes determinization of the probabilistic problem. And so this is a transformation of the probabilistic problem where every possible outcome of a stochastic action becomes its own separate deterministic action. And then we can show that if a condition is a landmark in this determinized version, it must also be a landmark in the original probabilistic planning problem. Therefore, we can use all those classical landmark extraction algorithms on this outcomes determinized domain to give us a sound method for generating both the probabilistic landmarks themselves and the orderings between them for the probabilistic planning problem. So with a way to generate probabilistic landmarks, we can now introduce our algorithm, LAMP. And the central idea is to use landmarks as subgoals. So we're decomposing a single large planning problem into a sequence of smaller ones. So instead of trying to find one long policy to the final goal, LAMP traverses that landmark graph. It learns a policy to achieve landmarks one by one. And so this is kind of like a form of temporal abstraction, similar in spirit to a lot of hierarchical planning approaches, where achieving a landmark is kind of like executing a high-level macro action. And so in the ideal case, this is a powerful technique. It can lead to up to exponential speedups. So basically, rather than searching for one big solution of length k, one big solution of length d, this could break up the problem into k subproblems, each with a solution of length d over k. And then you would, at the end, combine those solutions to get a solution to the entire problem. Each of those subproblems would be exponentially faster, and so this is a best case scenario, obviously, but it kind of illustrates the potential of this decomposition approach. Okay. Here's a more detailed look at the LAMP algorithm. So at its core, LAMP is an implementation of UCT. It performs a number of rollouts from the current state to learn Q values, and those Q values guide its decisions. And so this algorithm operates at two levels. So first, at the very beginning, or I guess after a landmark is achieved, it has to select the next landmark to pursue. And so it treats this as a planning problem itself, learning a Q function to select the most promising next landmark from the available leaves in the landmark graph. After it selects a landmark, it must select the actions to achieve that landmark. And this is that core planning step. This kind of hierarchical structure, selecting landmarks at a high level, selecting actions at a low level, that's the core of LAMP. That's the core of the LAMP algorithm here. It's also important to note that this only adds pretty minimal computational overhead. So building that landmark graph is a one-time setup step that you do at the beginning. And then during search, the number of additional nodes that you visit during each rollout is at most the number of landmarks in the landmark graph, which is small relative to the size of the state space. Okay, a critical part of LAMP is how it decides which actions to take. So as with standard UCT, we use rollouts to learn Q functions that estimate the value of taking each action. And so QG is the reward of selecting an action with respect to that final goal G. This selection policy would be the one as used in standard UCT, and it only considers that final goal. It doesn't benefit at all from landmark guidance. Now, the idea of LAMP is to use those landmarks to decompose the problem. So to do that, we additionally keep track of separate Q functions for each landmark phi. So Q phi is a landmark. Q phi is the reward of selecting an action with respect to that subgoal phi. So if we select actions solely focused on achieving the next landmark, that's fast because it's a much shorter horizon that you're searching for, but it can also be short-sighted since the shortest path to a landmark might actually lead to worse states for a future subgoal or even the final goal. And so there's kind of a trade-off to be had between quickly achieving the intermediate landmark versus making longer-term progress towards that final goal. And so to tune that balance, we introduced a greediness parameter. We called it alpha. So if alpha is 0, we say that the policy is non-greedy. It ignores landmarks. It's entirely focused on that final goal. This is standard UCT here. If alpha is 1, we say that the policy is fully greedy. It focuses exclusively on achieving this current landmark phi. And so this can converge quickly, but again, it suffers from that short-sightedness issue that I just described. So our algorithm, LAMP, generally uses a balanced approach. So it chooses some alpha between 0 and 1, and that considers both the intermediate landmark and the final goal when making its decisions about which actions to execute. So it does so using a weighted combination of those Q values. Yeah. Okay. So some results. Does this approach actually work? Well, this is one sample result from the probabilistic blocks world problem that we tested on. This graph shows the average cost on the y-axis and then the alpha value that we chose on the x-axis. That's the alpha parameter. Each of these lines represents LAMP running a different number of rollouts, so it ranges from 5 rollouts to 5,000. And so the number of rollouts basically represents the amount of work done to learn those queue functions. In our plot, the lower the cost is better, so it's no surprise that as you perform more rollouts, generally you get a lower cost. Now, all the way on the left, alpha equals 0, that's the baseline, remember, so this is standard UCT without any landmark guidance. Standard UCT is asymptotically optimal. So as the number of rollouts grows, as it approaches infinity, you will eventually converge to an optimal solution. But in a large problem, this can take prohibitively long. What's interesting is that if we introduce landmark guidance by increasing alpha, we can also see significant performance improvements, achieving much lower cost solutions. In fact, just by adjusting alpha, we can sometimes achieve an improvement on par with increasing the number of rollouts tenfold. If you look at that blue and red line, if you go horizontally from that, you go horizontally here, you can see you achieve basically improvement equivalent to a tenfold increase in the number of rollouts. The problem is, if the algorithm becomes too greedy as alpha approaches 1, the performance can also degrade. And so this happens because the algorithm becomes too short-sighted. So that's the core issue here. There's a balance here. We tested the algorithm on 5 other domains and an array of problems in each domain. And across a large class of these benchmark problems, we found that using landmarks consistently yields solutions better than standard UCT. And the optimal alpha value is usually somewhere between 0 and 1. There's some sweet spot in the middle. It actually varies across problems, so the optimal alpha value is problem dependent and domain dependent. And so this demonstrates that there's a balanced use of landmarks that provides the most effective guidance, especially when you're time constrained and you have a limited compute budget to perform rollouts. But it also paves the way for future work that could investigate how best to choose alpha for a given problem, or perhaps more sophisticated adaptive alpha schemes for planning. Okay. Of course, this approach is not without its limitations. I just mentioned this. The primary limitation is that LAMP can be short-sighted, which is particularly dangerous in problems with deadlocks. So LAMP compromises completeness, so it may fail to reach the goal even if a safe solution exists. So if you just consider this example state space with the initial state on the left, the goal on the right, and then phi is a disjunctive landmark that's satisfied by those 2 states within the dotted lines, S2 and S3. So a fully greedy agent, alpha equals 1, might choose to go along that bottom path because it's the most direct path to achieve that landmark. But this actually increases the overall cost of reaching the goal. So a balanced or a non-greedy agent would be more likely to go along that top path, which is the better action to take, even if it is a less direct route to that landmark. So in our experiments, we saw this exact behavior in several problems with deadlocks, and just based on this example here, you can construct a whole class of planning problems that kind of exhibits the same issue. So you can pathologically construct problems where any greediness at all would lower overall success rate, lower the performance of the planner, because landmarks would basically always mislead the planner towards unsafe or deadlock states. So this highlights the importance of tuning that alpha parameter to the specific problem at hand. Okay. To conclude, our work makes several key contributions. We formalized probabilistic landmarks for MDP planning and then provided a method for generating them via determinization. We introduced LAMP, which is an algorithm that uses these landmarks within a Monte Carlo search framework to decompose problems and guide search. Our experiments show that a balanced policy in LAMP that's tuned with this alpha parameter can significantly outperform UCT, especially in large domains or any time settings where planning time is limited. But our work also provides strong evidence that landmarks are an effective form of heuristic guidance for probabilistic planners. And so future work, we believe there's potential in exploring methods for adaptive alphas that change during planning or integrating deadlock detection to make that greedy search safer. For those interested, there are formal proofs and a deeper analysis of the algorithm in the paper and their full experimental results. But thank you for listening. Happy to take questions.
Thanks. Really good talk. Thank you for that.
Thank you.
So I just had a question about backpropagation. So you maintain the Q value for all of the landmarks
Yes.
at once, at all times while you're doing rollouts.
Yes.
And then when you backpropagate, you're checking whether each of those landmarks is achieved in that particular rollout. Is that the...
Yeah, so basically along that path, you encounter rollouts during you encounter landmarks during your rollout, and then with that reward value you get at the end, you backpropagate it to all those landmarks that you encountered.
Yeah, so any landmark that was on that path.
Exactly.
Okay, and you mentioned disjunctive landmarks. So what happens if you achieve one of those? Do you then cut the remaining ones in that set from your landmark set?
Do you mean achieving
So one of a disjunctive set where you don't need to achieve all of them.
Then the entire landmark is considered achieved at that point.
Yeah, okay, awesome. Thank you.
Any other questions?
Landmarks of landmarks, like in a kind of recursive phase.
Sorry.
Like you take every subgraph and then you plan landmarks there and so on.
A landmark of the landmark graph? I haven't considered that one. I don't have a good answer. I don't know.
How big are the landmark graphs?
Typically, so I think this is the landmark graph for this exact problem. They can get large, but typically they're much smaller than the state space. I don't have a good quantification of how large they are. It depends on the problem, of course.
We have time for a couple more questions.
Maybe I missed this, okay, but so a landmark here, it's a condition has to be, it's going to be true in all executions of a solution policy, or it's in some execution of every solution policy?
So a probabilistic landmark is true in every execution of any solution policy.
Okay, but that's a lot to ask, right?
Yes, it is. It's a very restrictive definition. That's right.
Okay, okay.
Have you considered using the probabilities associated with some of the facts to define?
So you mean a landmark that has to be achieved with some probability?
Correct.
We considered that. We felt this was a simpler mechanism for first try at this. I think that's for future work.
All right, with that, let's thank the speaker again.